calculus has two main branches, okay? Calculus has two main branches that each answerer is specific, but somehow related problem. So let's see. The first problem, which you won't really see until university. So one of the questions calculus asks is you take a function, you sort of shade some area underneath it, calculate the area, right? So it could be any sort of kind of curve, like you can have as many turning points or like this fancy curves and stuff underneath. And, you know, you try and figure out what the area is. It doesn't seem obvious at all, right? Like they give us formulas for areas of like circles, squares, triangles, like easy shapes. This is not an easy shape at all, right? So you kind of imagine that we need completely different tools to find that kind of area. So this is the calculus we're going to concern ourselves with for the rest of the course, right? So given any function, given a function, can you figure out what the slope is at a given point? And that is what differential calculus attempts. The differential calculus concerns itself with the question, given a function, can you find the slope at a point? If you decided to read the book on yourself or anybody else, they talk about things like instantaneous rate of change and blah, blah, blah. It's not wrong. It's just, I feel like it kind of complicates what's really going on here, right?
So let's just look.
Example, slope. So let's say over here, slope is 2, right? It makes sense because it's how steep the line is. For a straight line, the steepness is the same everywhere. All right. Slopes of y equals 2x versus y equals x squared. So let's look at our best friend here, our parabola y equals x squared. The first function you really learn that is not a straight line. If we compare a straight line, it's the same steepness everywhere. But if we compare it against a curve, the steepness sort of changes wherever you decide to pick your point, right? So for example, over here, like right at the vertex, it's like, I'd say it's flat almost, right? Like if I were to look at what the slope looks like over there, if I pick the point over here, my slope would kind of be negative because if I'm matching where the curve's going, it's going down, right? Over here, it'd be going down as well. Over here, it'd be going down, but not as much because you see it's slightly curved. And on this side, it's positive now because it goes that way. So the slope of a curve changes depending on which point of the graph is selected, right? So like I said, down here, the slope is like flat. Over here, my slope is kind of, at this point, you want to take a ruler, right? You guys see what I'm doing, right? You sort of take a point and you sort of like draw a line against it. It's a special kind of line. It's the tangent line. So the slope of a point on the curve is the same as the tangent line. If you decide to look this up somewhere else, you might hear somebody else saying, instead of saying, what's the slope here, what's the slope of the tangent line, right? Same thing. The function changes. So like sort of goes curving and it goes ups and downs and stuff. So you can't, there's not a single slope across the whole graph. You kind of have to figure out what the slope is at a specific point. So you can see, like right off the graph, right on the graph, you see that it changes. It's not as steep at the bottom here. It gets a lot steeper as you go up, right? Depending on what x is, the slope of x squared is different. Okay. How many points do we need to find the slope? We need 2 points, right? So say if I wanted to find the point at 1 here, I only have 1 point to work with. If you hold up your ruler against it, we only get 1 point, right? On obviously we already started playing around with these things. If I go y2 minus y1 over x2 minus x1, and I use the exact same point twice, so that's not allowed, right? You can't use the same point twice on the slope because you end up with 0 over 0. You're dividing by 0, right? So we're stuck. Where do we go from here? We can estimate though, right? So far, without calculus, what we can do is estimate. So let's just estimate. Let's estimate. So I'm going to take 1 and 1. And let's just pick a point close to 1. Like close enough, like if you stuck your ruler to it, like it looks like your ruler's hitting 2 points. Something like that. So maybe like 1.1. I wouldn't know what the other one is, right? So it would be 1.1 squared because we're on x squared. It's x squared, so we have to square whatever it is. So 1.1 squared. All right, so let's try that. 1.1 squared. 1 squared is still 1, so I don't need that. 1.1 squared minus 1. 1.1 minus 1. Right? So 1.1 squared is 1.21 minus 1 over 0.1. Okay? The denominator actually tells you how far apart the points are. You see that? So my first point and my second point, they're like 0.1 width apart. And that's kind of like good for estimation. 0.21 over 0.1. Let me go find my calculator. 2.1. 2.1. So over here. All right, can I write m for slope? You guys remember, right? Okay, so let's do the same thing at 2. So at x equals 2, estimate. With same thing, let's do 2 and 4, right? And 2.1. We'll just keep them 0.1 apart for now. And whatever 2.1 squared is 4.41. So if I go 4.41 minus 4 divided by 2.1 minus 2, your denominator will still reveal that my two estimated points are 0.1 apart. And 4.41 minus 4 is 0.41. So now we have 0.41 divided by 0.1. Should be 4.1. So over here, the slope is 4.1. Are we seeing a pattern? Are we not? I don't know, right? Like 2 points is too early to tell, but it looks like this is roughly double of that one. We can go one more. Estimate width. Let's see, 3 and 9, right? So 3 squared is 9, and 3.1, and whatever 3.1 squared is, 3.1 times 3.1 gives us 9.61. So we end up with 9.61 minus 9 all over 3.1 minus 3. So you have 0.61 all over 0.1, 6.1. Okay. So I thought I was going to go 248. It's going 246, right? So 2.1, 4.1, 6.1. So the slope on here is 6.1. And what I want to do is, because the slopes are changing depending where we are at, let's plot them. Let's plot the slopes. Let's plot the slopes. Just pretend that's a parabola, okay? So when x is 1, the slope is 2.1. When x is 2, the slope is 4.1, approximately. And when x is 3, the slope is 6.1. So it's almost like we got a new formula. So by plotting the slopes, we got like a new line, right? We got some kind of new formula. Theoretically, right? If I were to pick a point on this graph, say if I were to extend this to 4, whatever we get, assuming it'll probably be 8, right? I'm just gonna say. So at x equals 4, the slope will be 8, right? Which you can picture on the parabola like a really steep line with a slope of 8 up there, right? So this new equation and formula is basically the cornerstone of differential calculus, right? So this is called the derivative. The derivative is the equation or formula that tells us what the slope of a function is, right? It will get a bit more complicated than this and that, but we're going to keep circling around to that, right? The derivative gives you the slope on a function, right? But obviously, the way we have it right now, it doesn't feel like a proper formula because we just did a lot of trial and error, right? We just did a lot of estimation. That's where we have to introduce other tools. Can we be more accurate? So let's try a 0.01 gap. So over here I have 2 and 4, and here I have 2.01, and whatever 2.01 squared is, right? Ooh. 4.0401. So that means my slope is 4.0401 minus 4. 2.01 minus 2. 0.0401. 0.01. So it's like 4.01, right? Let's just try one with a couple more zeros. Oh, 4.0004. So you can sort of tell, right? My points, let's say this is Andy, right? So Andy going to be a bit closer now, right? Like that's sort of close. You can find my squeeze ruler into both points. 3 zeros is 4. Minus 4 there. 2.0001. Let's see. 0.0004. 0.0001. So you can tell approximately we get 4, right? So I think the best estimate that we can get is 4 if we keep the gaps like steadily shrinking, right? If we keep shrinking our gaps, we can get more and more accurate answers. But it's not ultimately the best thing we can do because we're still estimating at the end of the day. We don't want an estimate, we want a definite answer, right? So based on the tools we have now, we can't get better answers because we're limited to estimating, right? Estimating smaller and smaller gaps. We need something to help us analyze functions when the functions sort of get really small, when the gaps get really small. And, you know, kind of like a microscope or like a magnifying glass for your function. That's what we need. And that tool is called the limit. Everything that I said so far, I will repeat at a later point. It's just sort of like to get us a feel for what calculus is trying to do in the first place. What differential calculus is trying to do in the first place is trying to figure out a way to find slopes on functions, right? Based on everything we've learned so far in high school math, the only way for us to find slopes on functions is to do all of these awkward, like, guess and check methods, right? I don't want to guess and check. I want to actually find a formula that connects to the slope of my function, right? As you can see here, the graph on my right, eventually we'll figure out that this formula gives us the slopes of my parabola, right? Interestingly enough, we see that the slopes of my parabola change, right? How is it changing? It changes according to this formula, right? I can't do any of that right now. I can't even do any of that yet. I feel like I'm jumping ahead if we don't talk about limits first. Okay, so we're going to close the book for now. We're going to pause this portion for now, and then we're going to jump into limits. We're going to do some limits and then come back to here.